I told you about some cool electrochem related t-shirt ideas I have. So I'm going to share with you. Let's see if I can pull it up here quick. These are just some fun, not that we have to use them as t-shirts, but they're fun ideas. Let's see, I think this will work. Can you guys see that? So here's some good chemistry humor.
Is it bad that I get it, but I also still I only know it because you told me?
Yeah, well, that's okay. I mean, the great thing about this one is that there's kind of like 2 jokes built into it.
Facts.
So on the top, of course, we have the non-standard hydrogen electrode, so just the He. So he said, you've got a lot of potential. And she said, nah, it's quite standard, really. That's pretty decent, I think. And then for those of you who any of you like The Office, the TV show?
Yes.
Yeah. What about this one?
100%.
I love it. I literally, this is the one I like.
So this is like office chemistry humor, I guess. I don't know. There'd be plenty of people that would be like, what? I don't get it. But, it's a pretty good one. So something to brighten your day, hopefully, with there. Not that we're actually going to make t-shirts, but, now you have some ideas for cool chemistry pun t-shirts going forward. I like both of them. This one's a little bit more to the point, perhaps, and kind of fun. All right, back into chapter 15. I took a look through chapter 15 and looked through our learning objectives to help give you guys a little bit of focus here. We are going to primarily focus in on sections 1 through 6A, which means that we are going to completely skip sections 7 and 8 out of the chapter. They're not really included in any of the learning objectives whatsoever. And I guess I forgot to look ahead to the homework, but let me see here. Chapter 15, homework. There's a little bit on standard addition in the homework, it looks like, and some on ion selective electrodes, but not really so much on like solid state electrodes and other. They seem like just it's a little bit too specific for what we're doing. If we had been in person, I maybe would have, given a half-day lecture or something like that on some of the content, but I think it's not worth it. I also will mention that from section 6B, that's pages 356 to 363. There's a little bit of vocabulary in there that I think is useful, but beyond that, we won't worry about it. So let me give you the examples of the vocabulary that you'll want to be potentially familiar with. Let's see. They're listed here on this slide, but just being able to identify solid state ion selective electrodes. This would be sort of textbook reference sort of stuff. So not the sort of thing that I need you to be able to specifically like diagram or explain the chemistry of as somehow different from other ion selective electrodes, but just sort of knowing the terminology. You'll see them listed here in the vocab. You'll also note, if you care to take a screenshot of this slide, that this is a pared down list of vocab coming from the end of chapter terms, omitting those that come at the end of the chapter that we just aren't going to talk about. Also omitting some vocab from earlier chapters like matrix and standard addition, which are talked about again in this chapter. Only omitting those because I assume you already know them. They're not new. So not things that you need to be so concerned with, okay? Any questions about any of that so far?
Yeah, quick question. So on the homework, it lists chapters 15 and 17 for homework number 8. I'm assuming we're just gonna do chapter 15 homework.
Let me take a look at chapter 16 quick. I think I keep a list. I highlight the problems that I've placed on the homework. Although in this case I didn't for 16 and 17.
Wait, so for homework 8, there's still more chapter 14. So technically we have 2 homework assignments on chapter 14.
Yeah, is it the same problems?
Those are the
for
same
chapter-
problems from homework 7.
Good.
Yeah, so just do them, attach them to whatever homework, due date makes sense for when we finish. We're done with chapter 14 now, so is that going to be homework 7 makes sense for chapter 14 problems?
Yeah, that's due to, or it was or is due today.
How many of you are done with those chapter 14 problems already? Anybody not done with them?
I'm almost done.
Okay, so yeah, just to put those on homework 7. Homework 8, let's just do the chapter 15 and call it good. I mean, I don't hear any complaining. I see Corbin there celebrating that decision. I think that there's some value in the rest of this. The redox titrations, of course, would be useful to us in the grand scheme of things, but they're not worth losing any sleep over. And at this point, it's not that I want to encourage us to coast to the finish, but I'd rather see us try to do really well at the things that we're doing rather than trying to fit more stuff in. So whatever time that frees up for you, I hope you'll invest it into your final lab project and your faith learning project, and just making sure that you get all of the other things done for your homework and whatnot. So, so that kind of simplifies those down. We may still come back to, depending on how quickly we move through, I may talk briefly next week about some of the ideas coming from chapter 17, partially because one of them is a lab that we would have done using a platinum gauze electrode, and it's pretty straightforward. We actually could sort of talk through it with diagrams, and I think you would understand the entirety of the lab from that. So we may come to that, but for now we won't worry. We will say that there's no homework on any of the 16 or 17. And whether we get to talk about it in class or not will be a matter of timing. Okay, so that hopefully kind of sets up our chapter 15 adequately. From there, we have, of course, you have some learning objectives. I should make note that there's a learning objective I would like to modify just ever so slightly. Let me see if I can find it. Here we go. It's this learning objective on the top of this current slide. I think it's like the 3rd or 4th learning objective, where it asks you to draw or describe how 2 electrodes can be used to determine the concentration of a specific chemical species. I want to add to that something that probably isn't a surprise, but that you should be able to do this mathematically. We are going to do this, and you have already done it. And so this is on your consolidated or shortened list of objectives that I posted onto Moodle, not the expanded ones at the beginning of the chapters. Okay, so we should add to this then, I typed it different in the list. I modified it, concentration and solve mathematically. Okay, let me move this down. There we go. This is something we're going to do anyway. I'm not just gonna like expect you to figure it out, but it's also sort of the point of taking a look at it is that we can use galvanic cells or electrochemical cells to solve for unknown concentrations of chemicals. We do that with a pH probe, which we'll examine in a little bit more depth, but we can also do it with other types of electrodes. And so being able to understand some of the simple math behind that and set up those equations, which are just equations like the Nernst equation that we've already seen, That's kind of a critical part of that. Okay. Okay, let's take a look back here. Convert between different standard reference scales. So this problem here is not on your worksheet, but I think this is the easiest way for us to address what we otherwise see in the learning objectives and in the notes. I did, I think, 3 or so of them for you in the notes. These are the other 2 from that same problem. So if you take a look at the end of chapter, what you'll note, I'm going to switch to my iPad from there instead. Here we go. Let me share my iPad screen. Okay, I think we're live with that now. So these, if you look in the notes and compare them to problem 15.2, you'll note that I did like A, C, and E in the notes. So what I would like for you to do, I also here included a snapshot of figure 15.6, which is just our number line. That's how I did it in the notes. If you want to go back to that same slide, I've copied and pasted problems B and D. I'd like for you to go through right now and do these independently so that we can sort of put to bed this learning objective and you can say, yep, got it done, move on. All right, I have B up here on the screen. I'll walk us through how I did it. I tried to add some of my extra notes. So make sure you have that one done. I guess I didn't verify it ahead of time. I'm looking in the back of the book right now to just make sure that I did it right. 15.2. Yep, okay. So let's take a look at my solution for this. I'm not going to do part D. We can look in the back of the book and verify that you're getting that correctly also. But what I started with on my diagram here was my number line. We note that in this particular problem, it's saying it's versus the silver chloride. So I set that one to 0 on my number line and then labeled the other voltage. So essentially the green is the silver chloride scale. Notice that we have a similar thing going on in the figure where this is a standard hydrogen electrode scale. But because we aren't in that scale, I'm drawing the number line as the other scale, the one that we happen to be operating in. And then we're switching to be versus the standard hydrogen electrode. So all I did is I went and I looked. You can pull it from this diagram. You can pull it from another problem. If you know the value, you can pull it from that. But notice that the difference between the silver chloride and the standard hydrogen electrode, we can pull from this scale. It is 0.197, where the silver chloride is larger. It's 0.197 greater than the standard hydrogen electrode. So that meant in switching the scales, this becomes negative 0.197.
Is it frozen for everyone?
Yeah, he frozen.
Yeah.
Am I frozen? Hello? Are you guys there? Hello?
Oh, he gone.
Oh, he's back.
Oh, he's back.
You're muted.
Okay, I don't know what just happened. Where did I lose you guys?
You were still going through 5.2b, and I'm not 100% sure.
I
Okay.
think that you were looking at the scale and you already solved B
Okay.
and you're kind of walking through
Okay.
the scale.
Let me walk. I'll try to pull that back up. I don't know if it's my internet or if Zoom just had some sort of critical failure or what, but okay. So I was trying to point out that how we set up these numeric values. Did everybody follow that? How I set up the number line and got the numeric values on there?
Yes.
Okay. Then I just made a couple of notes. These are my thought process, and I use them simply as a quick check to make sure that when I set up my math and solve the problem that I have the correct value. So what I'm noticing because of the number line is that this value where I'm trying to solve for the new voltage or new potential, it is larger than the standard hydrogen potential on the number line, so it must be a positive value. And then it's just the gap between the two numeric values. So I can quickly do some mental math and say, well, it's got to be about 0.08 volts. Okay. So that's what I did. Then I set up the math accordingly. It's possible, I don't remember really if Harris has some fancy equation he wants you to use. In this case, I'd rather not use a fancy equation. I'd rather rely on drawing the number line and just reason through the values that we have. So we end up with the math here as shown, and the value ends up being positive 0.086 volts. That does match with what we find at the back of Harris in the appendix. For part D, that's the other one, yeah. For part D, we end up with negative 0.021. Okay, I'm not going to set up the math on that one. Negative 0.021 volts. But there's the answer for it. You should be able to verify that you get both of those. Any questions about converting between scales? Pretty straightforward. Okay. Then let me pull up the next thing. 5.3, this is on your worksheet. So 5.3 says, suppose that you have a saturated calomel electrode. That replaces the silver chloride electrode in the figure on the right. So I've included the figure here on your slide for you. Calculate the cell voltage if the iron 2, iron 3 ratio is 2.5 times 10 to the minus 3. So what do we have to do on this problem? What do you guys think the approach is for solving this problem? Any initial thoughts?
Should
When
we
I
write
see-
the half reactions?
What's that?
Should we write the half reactions?
Yeah, so we could try to write some half reactions. Okay, so let's try to figure out what those are. Now we know that we have an iron to iron, right? Must be this one. Iron 3 goes to iron 2. Should be one of the half reactions. What is the other, what do we have as information about the other half reaction? Any thoughts?
Well, it looks like the silver chloride reaction.
I'm sorry, what was that?
It looks like the silver chloride reaction.
Yeah, so in the
Silver.
figure, it's a silver chloride, but it's telling us that we should do this for the standard calomel, right? So the other half reaction is just an SCE. And we know from our converting between scales that on the standard hydrogen electrode scale, this has a set potential. You could look it up in the appendix, or you could just check your values for these and you'll find that it is equal to positive 0.241 volts. That is the standard potential of a standard calomel electrode. And since we're using it as a reference electrode, it's under standard conditions. So this particular value, that one's going to get used the way it is in our equation. And this other one is going to have a Nernst equation, right? So hopefully we end up saying, well, that means that E cell is equal to our E cathode minus our E anode. Which one is our cathode and which one is our anode?
The iron's our cathode.
The iron is our cathode. Okay, so this is going to be used here to solve for our E plus. And then this is already here equal to our E minus. Okay. So let's set this up then. Our E cell is going to be equal to our E standard minus 0.05916 volts over 1 electron times the log of Q minus our E minus, or the 0.241 volts. So really all we have to do is I guess I could erase this here. We can substitute in the value. We know that our standard is 0.771 volts. So we just have to take a look at our value for Q. We're given this ratio of the two iron ions. Is that already written as Q? Or do we have to take the reciprocal of it?
I'm pretty sure you have to take the reciprocal.
What's that?
I'm pretty sure you have to take the reciprocal.
I agree with that.
I think we have to take the reciprocal of that. Because we have here iron 2 over iron 3, which means, and remember, Q is going to be equal to products over reactants. Products over reactants. So I think it looks like our Q is in the right orientation, the way it is. This is going to be equal to 2.5 times 10 to the minus 3. So what does E cell equal? Let's go through and do that math and confirm that we're getting the right value. I'll verify I'm getting it too. I get 0.684. Is that what you guys are getting?
Yep.
I think that's what we get from Harris also. Okay,
Can I ask a stupid question?
you can ask any question.
Perfect. So I am a little bit confused, and we talked about it, but I'm still a little bit confused on how for your E, like the cathode, we use the Nernst equation, but we don't for the anode.
Yeah, that's a great question, actually. It's not a stupid question at all. So notice that we have here, I'm going to switch color. Hopefully we'll be able to follow along because of that. We have the two half reactions we're looking for. One of them will be the anode, one of them will be the cathode, right? We evaluate up top here based on the two potentials that this is going to be our cathode. And we see that our concentrations, because of the ratio, are not at standard conditions, right? So that means that when concentrations are not at STP, we need a Nernst equation. But when they are at standard conditions, we don't use a Nernst equation. That's the whole point of the Nernst equation. It solves for the potential of a galvanic cell or half cell reaction under non-standard conditions. Now I want to give you the proof of this because this topic came up. It actually was something that I was contemplating the other day also during lecture, and we just didn't get around to showing it. Let's on the side here write out, okay, E cell we had is equal to 0.771 volts minus 0.05916 over 1 times the log of Q, which we said was Fe2 plus over Fe3 plus, right?
Yes.
What would that Q become under standard temperature and pressure?
1.
1, right? Because each of those concentrations is equal to 1 molar. Notice that even if we had a Q expression that was something along the lines of A squared over B, or A times B over C, or A squared times B over C times D cubed. You create some crazy version of that. What do each one of those become under standard temperature and pressure conditions?
Would they all just be 1?
Yeah, they all become 1. Okay. Log of 1, what is that equal to?
0.
0. So now all of a sudden, under standard temperature, that portion of the Nernst equation cancels out, and we're left with nothing but E standard cathode. For the other half of that, that means that then we're getting the exact same thing where it's possible we would have for the anode a similar expression, but we're just getting rid of the Q correction, if you will. Under standard conditions, it's still there, but it's equal to 0. Its magnitude becomes 0. So to wrap that up, the fact that this is the standard Calomel electrode tells us that it's under standard conditions. Does that help?
Yes, thank you. That makes a lot of sense.
No problem. Thank you for asking the question.
So will there be problems in which we have to do the Nernst equation for both the anode and the cathode?
Certainly there could be. Now, that would be a problem that would not be one that falls under the using a standard electrode as a chemical probe to find another concentration.
Yeah.
Right? So under standard conditions, that's why we choose them. And that's why we focus basically on these 3 types of reference electrodes. The standard hydrogen electrode, the standard calomel electrode, and the silver-silver chloride electrode. Those really, those 3 are going to be your primary standard reference electrodes. And they're going to be used in electrochemical cells where you are trying to solve for other values. But really, this is just a continuation of the work from last chapter. We are just now saying, but hold on a second, let's just control some of the parameters so that they are known and we can limit the number of variables in the equation. If we can do that effectively enough, then we're able to limit it down to a single variable, that being 1 concentration of 1 chemical species, and then the entire potential of the cell is dictated by that 1 chemical species. Which means that if they're proportional, we can measure that concentration based on the potential output of the cell. And that's essentially how a glass pH electrode works. All but 1 concentration are fixed and known. We'll talk about that, I think, next class period. We're going to get into a couple topics, including junction potentials and ion selective electrodes, where pH electrodes are a specific type, the most common type of those. We'll talk about those 2 things, I think, on Friday, but that's just sort of a little glimpse to what's coming. Okay? Any other questions about this problem before we move on? I've got what I'd like to do is have you guys take just a little bit of time to look into a couple of topics and then kind of report back as a group. No other questions? Okay, then here is what I have for you. Let me pull this up. This relates to one of the other learning objectives, describe the function and design of several reference electrodes. And really it gets into the differences in types of electrodes. So what I would like to do is I'm going to randomly assign 3 working groups right now. And I'm going to give you just a short amount of time. We have about 30 minutes left of class. So I'm going to give you about 15 minutes to go and take a look through Harris. This is going to be found, this material will be found in the first sections of chapter 15. In fact, specifically, I think just the first 2 sections. Let me verify this. Yes. So the first 2 sections, it's about 4 pages worth of material in Harris. Pages 338 through the bottom of page 342. There's a lot of figures. One of them is the intro to the chapter, things like that. And then here's some suggestions of other locations to look. And I would like each of the 3 groups to focus on one of these. So group 1 will use Harris in combination with Wikipedia. Group 2 will use Harris in combination with the Gamry Instruments website. So Gamry is the instrument company that manufactured our potentiostat in our lab, and we use it for doing some calculations or some monitoring of ion concentrations in solution. And then the other one, I have this extended link here. What you'll notice if you just go to the Chem Libre Texts website, go to their bookshelf, then go to analytical chemistry, then go to supplemental modules, and just use each of these dashed sections as the sort of the path or the click path to get to it. You'll be able to find an article on potentiometric theory and reference electrodes specifically. I looked through it briefly, and I think that the 3 of these, in addition to Harris, provide some nice information that we can together bring together and try to offer up a complete answer to the questions above. So you may not be able to, in your small group, answer all of that question. I want you to try in 15 minutes to gather as much of the information as you can to answer the questions at the top of the slide here. And then we're going to bring that together as a group and offer the different information we found on these other sources as a class, okay? Any questions?